Welcome back again and again, guys. You can't get enough of these chemistry videos, can you? Well, the topic, I'm just kidding. I know you can. You already have had enough. But in any case, the topic du jour, salts versus molecules. So this goes back to the third unit. We talked about sort of like nomenclature. And in naming the salts, there's a different scheme than naming the molecules. Let me review that in just a second. But more importantly, I'm at the last slide of my document here. In any case, when I make a molecule, I take usually two nonmetals, two or more, often many, many more nonmetals, and they share electrons, covalent bonds. Electrons aren't transferred. There's no official formal charge plus minus. Yeah, I'll stop there. But then to say also salts, as compared to molecules, are formed when the ionic bonds between a positive and negative ion attract each other. A transfer of electrons when I maybe make sodium chloride from sodium metal and chlorine gas. Transfer of electrons. Rule of thumb, as soon as I see a metal mentioned, if I see a metal mentioned and the metals are listed first in a formula for a compound, if I see a metal listed first, it probably has a positive ion and we can call it a salt. That's a rule of thumb. It doesn't always work, but for our purposes it almost always works. So again, for the salts, remember dating back to when we talked about nomenclature for salts and molecules. Remember the +1 family, the +2 family, the +3 family, the -1 family, the -2 family. Noble gases don't do anything. Tin and lead like to do the 2 plus, 4 plus thing, and the metals in the middle, you have to specifically say what the charge on the oxidation state on the metal is, or you can be able to figure it out from the formula. If there are only two different types of elements in the compound called binary compounds, then there are just several choices. We could have two nonmetals, in which case you make a molecule. We could have a first or second family metal and nonmetal, making a type 1 binary compound, or we could have the transition metals and one of the transition metals and one of the nonmetals to make a type 2 salt, type 2 binary compound. Oh, by the way, there's no such thing as a type 3 salt. That's named incorrect. That's saying it wrong. If I had a type 3 binary, it would be called a molecule. Yeah? Yeah. In any case, oh yeah, here's a strange one. Well, it's not so strange, I guess. Aluminum's in the 3 plus family, and so I know it likes to be a 3 plus charge, and the oxide's in the 2 minus family. So how do I make a 3 plus ion match up with a 2 minus ion in terms of balancing the charges? Oh yeah, I take two of these and one of these. The name is simply aluminum oxide because I don't need a Roman numeral or anything di, tri, mono, whatever silliness, because this is not a molecule. Remember, we use the mono, di, tri, tetra, penta, hexa, hepta, octanona, deca, etc., 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 for the molecules, but not the salts. So if I see a metal right away, I know it's not a molecule. So metal is magnesium, the nonmetal is chlorine, chloride, or chlorate, or hypochlorite. In any case, this is a salt, right? It's not a molecule. As soon as I see the magnesium and the chlorine, doesn't matter if there's an oxygen there or not, I'm going to go ahead and call it a salt. Magnesium chloride, magnesium is in the 2 plus family, chloride's in the -1 family, and so I'm going to choose this one, right? Choice E. Chromium fluoride. I would guess I better specify a Roman numeral on that chromium because it's a metal in the middle of transition. It can have several different oxidation states. Fluorine's in the -1 family, but there are 6 of them. 6 -1s force the chromium to be in the 6 plus oxidation state, so chromium 6 fluoride. But that's a salt, right? Type 2 with a transition metal and a non-metal. Shoot, you can do that one. You can do that one too. What about the type 3 binaries? Or, it doesn't have to be binary. I could have literally dozens or literally hundreds of non-metals bonded together in a big organic molecule. Not a salt, as long as you don't have a metal involved. As soon as you have a metal involved, there's probably a metal ion, and the metal ion forces the counter ion to be negative, and then there's some kind of ionic stuff going on there. Anyways, this is not a salt because they have two nonmetals bonded together. So you might think I would say monoiodine pentachloride, but you don't have to mention the mono if there's only one of the first species, first element. So I'm going to say iodine pentachloride. There it is, choice C. This is naming, and you can do it. You would name this one as tetraphosphorus hexaoxide. Oh yeah, tetra means 4 and hexa means 6. So how about this one? And that's a molecule, not a salt. So why do we care? A lot of times we can classify compounds as and comparing them to each other by saying, well, if I have a metal and a nonmetal, it's going to make a salt and it's going to melt hot. There are large interparticle forces between the salts called lattice energies, and they melt very hot. Molecules, if they are if they are a solid, they melt very easily. Oftentimes they're gases or liquids. They're all nonmetals sharing electrons. With the salt, they have a metal and a nonmetal transferring electrons, except for the ammonium salts. But that's kind of an exception, but an important exception. Do you know what the ammonium ion is? Look some up. Look up Google ammonium salts. See what you see. See what you find. In any case, the salts will dissolve in water, usually fairly easily. There are exceptions to that, but in any case, salts dissolve in water to create ions and an electrolyte solution. But if the molecule dissolves in water, like say sugar or carbon dioxide dissolves in water as well, those molecules don't break up into ions. They do not create electrolytes. They're called non-electrolytes. They do not create ions when you dissolve them in water. If the molecule is lopsided in a sense, geometrically or electrostatically, that would allow it to boil. Hang on, I have a knock on the door. How embarrassing. Another good student interrupting me. That's awesome. Oh yeah, what was I saying here? If the molecule is polar, the interparticle forces make them sticky, might allow them to stick into a liquid or a solid. Therefore, they would melt or boil at higher temperatures than if the molecule was not polar. That's coming up in chapter 5 and very important, but we'll brush that aside for now and say, do the majority of these other distinctions between salts and molecules make sense? Hopefully so. If not, definitely ask somebody. Thanks guys, see you soon.